Started.
All right, hello. Welcome back to another Mathcounts meeting. Today we're going to finish the last few problems of 1990 team, and then we'll move on to 2016 state. So right now we have number 7, the natural numbers 1, 2, 3, dot, dot, dot are written consecutively. What is the 3001st digit written? So not like the 3001st number written, the digit written, right? Like if it was just a number, that would be extremely easy. It would just be 3001. So basically, how we can do this is all the one digit numbers, each of them is going to account for one digit for each of them, right? Because they're one digit numbers. And then the two digit numbers, each number that we write down, they're going to count for twice the number that we write down, the number of digits, right? And then same for three digits, and as we go on. So I mean, we can just start by like thinking how many one digit numbers are we're going to have, right? So we're not going to have zero, but we're going to have all the other digits. So we're going to have nine one digit numbers. So the number of digits that this is going to account for is just 9 times 1, right? Because they're one digit numbers. And then how many two-digit numbers are we going to have? Well, the first two-digit number we're going to have is 10, right? And then we're going to go to 99. That's going to be our highest two-digit number. And this is an inclusive range, right? So the number of numbers we have in here is going to be 99 minus 10 plus 1 because it's an inclusive range. Again, like if you have an inclusive range and you're wanting to find the number of numbers that are in here, you just subtract the two and you have to add one, right? If I didn't add one here, it would just say 1, but there are actually two numbers in the range 1 to 2. So doing this, it's just 100 minus 10, that's just 90, right? And then three digit is going to be 100 to 999. And using the same number formula, we're going to have 900 three-digit numbers. And then now you can start to see a pattern of like the number of digits or the number of numbers that you have for like some digit thing, right? Like one digit is going to have 9, two digits is going to have 9 times 10, and every time you go into the next digit, you're going to have 10 times the amount of numbers that you had in the previous digit, right? So so okay, so we can just do this by hand really, because I mean like it goes the number of digits for this stuff gets pretty big pretty fast. So like okay, so after let's just subtract this already. So after we go through the one digit numbers, we're going to need like 3001 minus 9 digits after we've gone through the numbers with one digit. So let's just subtract this. It's just going to be 3000 minus 8. So that's just 2992. And then after we've gone through the two-digit numbers, we're going to uh, we're going to go through 90 times two digits, right? Because we have 92 digit numbers and each of them have two digits, right? And this is 180. So after we go through the two-digit numbers, we're going to need to go through 2,812 more digits. And then we have 900 three-digit numbers. And so we're going to go through 2,700 digits in here, right? So after you go through the three-digit numbers, we're going to need to go through 112 more digits. And now, like clearly, our stopping point is going to be somewhere in the four-digit numbers, right? Because like the three-digit, if we went through all the three-digit numbers, we went through 2,700 digits, and if we go through the four-digit numbers, we're going to go through more than that, but we only have 112 digits to go through remaining, right? So now we can just look at like each four-digit number individually, right? So our first four-digit number is going to be 1,000, right? And next is going to be 1,001 and 1,002 and so on. And each of these numbers is going to account for four digits, right? So we can find the number of numbers that we have to go through by dividing 112 by 4, right? And this is just going to be 32, so um, that's just going to be 28. So we're going to have to go through 28 of these numbers to like reach the 112th digit, right? So like the 112th digit is going to be at the end digit of one of these numbers, right? Because like this is going to be the first digit that would go through, and this is going to be the second, and so this is going to be the fourth, right? And this is going to be the eighth, and so each of these last digits are going to be multiples of four, and 112 is a multiple of four. So we're going to be at some ending digit here, right? And so like with the first number, its last digit is its position times four, right? So if we're looking at the 112th digit, the position of the number that we're going to look at is going to be 112 divided by 4, which is 28, right? So if we find our 28th number of our four-digit numbers, then its last digit is going to be the 112th digit, which is the digit that we want to get, right? And then so if 1,000 is the first number, that's going to mean 1,027 is going to be our 28th number. And I mean, you can figure that out just by looking that to get from our number to our position, we subtract 999, right? So like 1,001 minus 999 would be our second uh, position. So we have to add 999 to 28, so we get 1,027. And again, we said that the 112th digit is going to be its first digit. So our 112th digit of our four-digit numbers is going to be 7, which is the digit that we wanted to find in the first place. So it's just going to be 7, which is our answer. Anything you want to say, Bill?
Nope.
All right. Let's move on to number 8. 200 lottery tickets are sold for $1 each. Three prizes are awarded in the amounts of $10, $50, and $100. How much money in cents does the lottery commission make per ticket? All right. So, okay. So what we can do is we can just find the total amount of money that the lottery made, and then we divide it by 200 lottery tickets, which is the number of tickets that they sold, and that would let us know the amount of money the lottery made per ticket. So so we need to find out the total amount of money that the lottery made, which is which the amount of money that they receive is going to be 200 tickets times $1, right? And then but they're going to be paying $100, $50, and $10, right? And this is all they've done. So this is just the expression for the total amount of money that they made. So and this is just $200 minus $100, just $100 minus $50, just $50 minus $10 is just $40. And then again to find the total amount of money that the lottery makes per ticket, we're just going to divide this total amount of money by the number of tickets that they sold. And this is just going to be $1 over 5, which means for every 5 tickets, they're going to make $1. And what does that mean? Well, that means they make 20 cents per ticket, right? Like if we converted this into cents, that would be 100 cents. Divided by 5, that's 20 cents. So our answer is 20 cents. That was pretty easy, much faster than the last one. All right, anything you want to add, Bill?
That was a pretty simple problem. There isn't really anything about it.
Yep. Okay, the formula S equals stuff gives the height S at time t times t of a projectile fired vertically from initial height s naught or s0. I'll just call it s0, and initial velocity as a v0. How many seconds will it take for a particle fired with initial velocity 128 feet per second from initial height 144 feet to attain the height 336 feet for the second time? All right, so basically it gives us a formula for a thing, and then it gives us some applied things. So like we just apply the stuff that they give into the formula that they give us. So we have S equals negative 16 t squared plus v naught t plus v0 t plus s0. And again, this is going to be the height of the projectile, and this is going to be the time, and this is going to be the initial velocity, and this is going to be the initial height. Now, the problem that they give us is going to be initial velocity is 128 feet per second. Um, Initial height S0 is going to be 144 feet. And we want to find the second time that they attain um, 336 feet. So basically, if we plug these numbers in, we're going to have a quadratic equation for t, right? So we're going to have two solutions for t, and we just want to get the second solution for t, right? Because it says it wants it for the second time. So we should just plug these numbers in, right? And I'm not going to count for units because they're all like the same units. So let's just plug it in. Um, we do have some pretty big numbers though. That should be fine though. So okay, we're going to move everything to the side so that we just have this equals 0. So then you know you can apply quadratic formula or you can factor and stuff. So we're going to minus 144 from no, we're going to minus 336 from 144. So that's just going to be the negative of 336 minus 144, which is just 192. So we're gonna have a negative 192 here, and that's going to equal 0. And then we should try to make these numbers a little bit smaller. We can see that all of them are even, so we could divide by 2 for all of them. So we're going to get negative 8t squared plus 64t minus 96 equals 0, and they're still all even, so we can we can see that they are all divisible by 8 actually, so we could just divide by 8. So that's just negative t squared plus 8t minus 12 equals 0. And just to get our a being positive, we can multiply by negative 1 for all of them. So then we have t squared minus 8t plus 12 is 0. And now we can just factor it, right? We can try to factor it. So we need our last two numbers to multiply to positive 12, but we need them to add to negative 8, right? So that's just going to be negative 6 and negative 2. Negative 6 and negative 2 multiply to 12, and they add up to negative 8. So that means we're going to have two solutions of t equals 2 seconds and 6 seconds. What's the second time? So that's just going to be 6 seconds. That's your answer. Anything you want to say, Bill?
So, right, this problem. Yeah, I guess it's just a lot of plugging numbers in and then just solving the pragmatic in the end. Um,
Yeah.
just make sure that you see that you can simplify this because simplifying will make your life a lot easier in this case.
Yeah. You don't want to try to do stuff with this like
Right.
factor or quadratic formula. That would be a lot of big calculations.
Yeah.
All right, let's just go ahead and move on. So, a rectangular piece of paper with length z plus 2x and width 2y plus 2x is cut. Some paper thrown away and the remainder folded with no overlap to form a closed box with volume xyz. Find the total area in terms of the x and y of the paper that is thrown away. Okay, so we have a rectangular piece of paper with length z plus 2x and width 2y plus 2x. And okay, so this piece of paper is cut and some paper is thrown away. Okay, and then the remainder. So the remainder is saying like the remainder folded with no overlap to form a closed box. Okay, so we're cutting like a thing here, like
Yeah.
a what?
You're right. We're cutting it into the
Yeah, okay,
shape
we're
of.
cutting a weird shape, and we're going to fold the shape, and the shape is going to form a closed box. And its volume is XYZ. And we're gonna have like some remaining part. If you guys have ever seen like this shape thingy, it's basically a cross. Oops. Oh, website delete the whole thing. Okay, whatever. Um, okay, it's this is pretty bad drawing, but basically it's like partition like this, and if you fold this together, it's going to form a cube. So basically, we're going to like cut out some shape kind of like this, but not exactly, right? Because it doesn't have to be a cube. And we're going to fold that into a box, and it's going to have volume x, y, z, and there's going to be some remainder parts of the paper that we don't cut out. Yeah, we need to find the total area of that paper. Um, all right, so I mean, we could start off by so we could start off by thinking that our shape is going to be something like this, and we could just use this, but keep in mind that like it's not the sides are not going to be all the same, right? It doesn't have to form a cube. So if we think of our shape like this, um, we can say that this side is going to be um, or actually, does it have to border the rectangle?
It doesn't seem so. It just wants the outcome, which can make a closed box of volume XYZ. It doesn't have to border the rectangle.
Uh, then
So what
Then
I think we should do is
okay, yeah,
we're looking for the total area of paper that is thrown away. So the paper that we have left over, it's the surface area of a closed box with volume XYZ, right? So if it's a closed box, if we find the surface area, you can just subtract that from the overall, and then find how much we cut away.
yeah. So I mean, like we can also try to find the surface area of our box, right? The surface area of our box is going to equal the area of our cutout shape, right? I mean that like you can just see that when you fold it. So if we find the total surface area of our box, we can just subtract that from the area of our original rectangle, and that would equal our the area of the paper that is thrown away. So we can try to find the surface area of the box. Um, so we have a box, but we don't know its length. All we know is the volume, right? Um, the volume is XYZ. Uh, and I mean, I don't know. Do you see a way to find the surface area here?
Well, if the volume is XYZ, we can just, without loss of generality, we can say that the box is, has side has a side length of X, Y, and Z. We can do that.
Um, well, we can assume that, but not without loss of generality. Like we can try that as a solution, but it doesn't have to be
Right,
it doesn't have to be the sides are X, Y, Z, right? I mean, we can try it.
right. Yeah, okay, it's not without loss of generality, but yeah, we can still try it like that. That's just one option that works. All right.
Sure. Okay. So we can start by we can start by thinking or start by assuming that the sides are X, Y, and Z. Now, if we do that, the surface area is just going to be 2xy plus 2yz plus 2xz. But do we have to like check if the unfolded version of this box like can fit into here?
Um, if you
I
think
mean,
about it,
I
yes, it will. Yeah,
okay, well
it most likely will. From what from what I'm looking at, it
most
will.
likely. Um so okay, so let's think about like unfolding this into like this kind of shape. So let's think of we're going to take this top this top this top rectangle and we're going to fold it out. So this top rectangle is going to be this rectangle right here. So then that means this side length would be x, this side length would be y, and this side length would be z. Okay, this side length would be z. And and we need to see if this can fit in our rectangle thing. So this whole this whole side is going to be 3z long, and this whole no, I'm bad. This whole side is going to, so this is symmetrical, right? So that's going to be z, but this is x. So this side is going to be 2z plus x long, and this side is going to be y, and these side lengths are z, right? Yeah. No. No, this side length is y, but this one, wait, what? Yeah, this side length is z and this side length is y. That's a little bit
Right.
weird.
Yeah.
So okay, so just like imagine it like folding back up, right? When we're folding it back up, this this rectangle is going to be this rectangle, right? And this side length is z. And so like this rectangle is going to form a back rectangle right there, and this side right here is going to correspond to this side, so it has to be z. And this side is going to correspond to this side because this is our top rectangle, so that side has to be y. And this side has to be z, right? Because it's this side. It's talking about this z, right? And like it's like if you fold it up, it has to correspond to this side. It has to be the same as this side. And then this side length would be 2z plus 2y, right? All right. So does that fit into a rectangle? Um, I mean, I'm thinking like not necessarily, right?
If
Like,
if you think about it,
yeah.
if you fold it a different way, you probably could because if you have the longer side, the four squared one, the of with z, it will fit if you think about it.
Yeah. Okay. Okay. Yeah. So okay. So so this way of folding it. Okay. So first off, the current side length that we have right now it does not necessarily have to fit in this thing, right? Because we have no idea how y and x are really related, right? Um, but so this is one way to unfold the box, but you can have multiple ways of unfolding the box, right? What we did right here was we took the top of this and we put it all the way out so that it was here. But like you can do this with like any side of the box. It doesn't have to be the top. So in each of those folding patterns would correspond to different total side lengths, right? So like we should test all of them, right? But if we test like if we do the same unfolding thing for all of them, that's going to take forever. So we need to think of a smarter way to do it. And there is actually a pretty nice way to think of it. And it's that for our box here, the sides x, y, and z are totally interchangeable, right? We like all of our formulas for this, which is just really the volume, is totally symmetrical, which means that we can interchange x and y, and it wouldn't affect anything, right? So like I don't know, like the um like it's not saying that x, y, and z are equal or anything like that, but it's saying like x, y, and z can be interchangeable and everything would still be the same, which means that with our formulas here, we can interchange x, y, and z like in here, kind of. So like it's like we have the set x, y, z, and basically we can put this into a new set, maybe say like z, y, x, and this would be saying that we change all of our x's to z's and we change all of our z's to x's, but we have to follow this pattern. We can't just like change just z's to y's, or I mean like just change z's to x's and not change x's to z's, if that makes sense. Um, so yeah, so basically we can do stuff like that now. But like if you look at these two if you look at these two expressions, they their format looks very similar to these sides, right? Because we have like 2 times something plus just 1 of something, which is that format, and 2 times something and plus 2 times something, which looks like that format, right? So we should try to see if we can change these variables so that it corresponds exactly to those. And if it does, then obviously this thing would fit in there, right? So we look here and we see that our z is the one with the 1 thing, right? So we should try to change our x into z. So okay, so we have x, y, z here, and we want to try to change our x into z. And then we look at 2x's in both of these equations, and nothing else is, right? And so we look here, we see that 2z is in both of our equations. So we should try to change z into x. And no, wait, what? Yeah, no, okay. We should try to change z into x. And then we see that 2y is just by itself on the thing. So we should just try to change y into y. And I actually got this right the first time I explained it, but that was just a total guess. But yeah, okay. So let's try to change our variables like that. So then we would have so z is into x, so that's 2x, and x is into x goes into z. So then this side would be 2x plus z, and then this side would be z changes into x, so that would be 2x, and y doesn't change. And now we can see that our formulas are exactly the same as these, right? 2x is the same as this, and 2x plus 2y is the same as this. So then this would fit into here, right? It would fit while touching the borders. So that means it is possible to fit this unfolded box into here with sides x, y, and z. Anything you want to say to that part, Bill?
Okay, so what Austin's done here is that he's rigorously proved that well, he's proved that the box, when it's unfolded, the box that we created can fit in the rectangular piece of paper. Under a time crunch, that's not something you necessarily have to do. You can just like um, assume that it fits in there.
Yeah, okay, I think it depends on how much time you have.
Yeah, if you're
Like if you have like no time at all, then just go ahead and assume that the sides are X, Y, and Z, and just do it like that. And assume that the sides fit in, or assume that the unfolded thing fits inside the rectangle, and then do it from there.
yeah,
If you have more time, I don't know. The proof is still kind of longish, and I don't know. Um, I don't know. If you have more time, maybe
but
try
don't
seeing if it will
but
work.
don't
But
spend like a ton of time on it because there's still
yeah,
other problems to do.
yeah. Or I mean, this is the last problem. If you've done all
Um,
the other problems and you think you're fine with those, and and you have some time with this one, maybe you want to try to prove it.
ag-
But like maybe like if you have previous problems that you were unsure of, and maybe don't spend as much time on this problem so you can go back and look at those.
and also like what you should do, what I recommend doing is just assume that it works at first, and if you have time, come back and prove it.
Oh, okay, yeah, that's actually a really good thing. Just assume like the most probable case.
And then
And then if you have time, you can go back and see if it will actually work. And if it works, then good, you already did it. And if it doesn't, then you can try to find the actual solution.
yeah,
All right, so yeah, so we did just prove that or the rectangular box with X, Y, and Z does like the unfolded part or one version of the unfolded part fits into our thing. So then we could say our box will have sides X, Y, and Z, which works with our volume, and now we just need to find the surface area, which is this. And then again, our surface area of our uncarved part is going to be this is going to be the surface area. The area of our uncut part is going to be or not uncut, like the remainder part. So yeah, the area of our remainder part is going to be the area of our starting rectangle minus the surface area of this box, which is this. So now we just need to like solve for that. Um, so the area of the rectangle is just going to be its sides multiplied together, which is this. And again, we need to subtract the surface area of the box. Okay, and then we should just FOIL this out. So we have 2yz plus 2xz plus 4yx plus 4x squared. And we still have the other stuff. Okay, and then we should try to cancel some things out. So we have 2yz and minus 2yz there. And we have 2xz and minus 2xz there. And okay, so we have 4xy here, and we have negative 2xy there. So then we can subtract, and we're gonna have 2xy plus 4x squared. And there's nothing else we can simplify here, so this is going to be our final answer. Or you can factor out the x, but I mean, who cares? So you can do it in both ways. You can see that on the solution has both versions. Uh yeah. Nothing else you want to say, right? Cool.
now it's just finding the surface area, so that's not really that complicated.
Yep. Yep. All right, so that was our last 1990 team problem, and now we're finished with all of the 1990. And Now we're going to move on to 2016 state. So I already have it here. We're going to start with the sperm problems. So let's just go ahead and do them. So we're starting with number one. Let a at b equals a over 2a plus b. What is the value of 5 at 3? Express your answer as a common fraction. Okay, this should be pretty simple. They give us a thing, and we just apply the thing, right? So if we have 5 at 3, it's going to be saying a is or 5 is our a and 3 is our b. So we just plug that in, right? So we're going to have 5 over 10 plus 3. So that's going to be 5/13. So that's our answer. Pretty easy. I'm just going to move on here. Okay, next we have how many rectangles of any side are in the grid shown here? Whoops. Okay, of any side are in the grid shown there. Okay, so we should again, if we have like a shape finding problem, we should try to separate it into finding different like different shapes, and then adding all of those adding all of those possibilities together at the end. So we should first look at our tiniest rectangle, which is just like 1 unit of this, and that's pretty easy to see that there are 3 of those. And then we should try to look at our this rectangle, but two of them put together, and that's pretty easy to see that we just have 2 of those. And then the longer one will have we'll just have one of them, which is just there, right? And okay, so now let's try this rectangle, and that's easy to see that there are 3 of those, and we can just there's nothing like special about like this rectangle, like I don't know, like you can just do the same thing with this rectangle that we did there, with this rectangle that by doing it here, right? So then we're also going to have a total of 6 possibilities for these kinds of rectangles, and 6 for those as well. And now we should consider like these rectangles like combined together somehow, right? So okay, so yeah, so now we should look at this rectangle where they're combined together, right? And we can see that like we can just do the same thing that we've done here, right? Like have it as 1, have it as 2, and have it as 3, and it would correspond to the exact same things, right? And so that would be 6 for it also. And I mean, there's no other rectangles we can make here. By doing this, we've looked at all of the rectangles. So then that's just 6 plus 6 plus 6, which is just 18. Anything you want to say there, Bo?
I mean, there's not really anything to say. This is really simple. It's just counting
Yeah.
that simple.
Okay. Yeah. Um. Okay. Number 3. Given 7x plus 13 is 328, what is the value of 14x plus 13? So it's pretty easy. Just solve for x with the first equation, and then plug in our value of x into there. So we just minus 13 on both sides, so that's going to be 15. And then we divide by 7, so that's just going to be 45, right? Okay, so if x is 45, the value of 14x plus 13 is just 14 times 15 plus 13. And we can multiply this easily by taking out a 2 from 14 and putting it into 15. So then we have 7 times 30. 7 times 30 is just 210. Then we just need to add 13. And that's just going to be 223. And oh crap, I did something wrong. Oh, why did I say 15? It should be 45. Yeah, because we got x equals 45 there. So, but we can still do get the 2 out of 14 and put it into 45. So then we have 7 times 90. 7 times 90 is just 630. and then we add 13, and that's just 643. So that's our answer. All right, anything you want to say, Depo?
No.
Yeah, okay.
These all these are at the front are very simple, so there's nothing really to, you know, just don't make dumb mistakes, I guess.
Yeah, like saying x is 15 when
Yeah.
it was 45. Okay, what is the median of the positive perfect squares less than 250? Okay, so we should try to find the our set of positive perfect squares less than 250, which is going to start with 1 squared, which is 1, and it's and we should try to find its ending point, right? So I mean, you guys should know that 14 squared is 186. That's pretty close to 250. But 15 squared goes higher. It's 225, and then we should try 16 squared, which is 256, but that's too high. So we can see that 15 squared 225 is our largest perfect square that is less than 250. So that means we're going to have, oh no, that means we're going to have our perfect square range is going to be from 1 squared to 15 squared, which is from 1 to 225. Okay, so if our so now that we know our range is 1 squared to 15 squared, we need to find the median of this set, right? So we can just think of it as like our set of our set of integers squared, and then find the median of the set, and then just find the square of that median, and then we will find our answer. So this set is going to be this set has an odd number of values, right? Because it's from 1 through 15. Its size is just 15 minus 1 plus 1. So it's just 15, right? That's odd. So which means its median is going to be one number in the very middle. And the number in the very middle is just going to be 7 squared, right? Uh, it's, um, oops. Actually, no. It's going to be 8 squared. Sorry. It's going to be 8 squared because 8 squared, 8 is going to be 8 is going to be 7 away from so 8 is going to be 7 away from 15, but it's also 7 away from 1, which means that it's going to be the middle of our set. So and as we said before, the middle of, because we have an odd number of numbers in our set, the middlemost number is just going to be our median, which is just 8 squared. So then our median is just 64. That's your answer. Anything you want to say, Bill?
Right. No, just be sure that you're doing the right thing when you're trying to find the median. Don't do what Austin did.
Yeah, I mean, I figured it out though. Right. Okay, yeah. Let's move on to number 5. So if x plus 5 over x minus 2 is 2 over 3, what is the value of x? Okay, so we have just a thing here. So what we can do is we can we can cross multiply. So we can multiply both sides by x minus 2 to get rid of the denominator of x minus 2. We can multiply both sides by 3 just to get rid of any fractions, right? So if we do that, if we multiply by 3 and x minus 2, we're going to cancel out this x minus 2, and we're going to have 3 on this side. And we're going to cancel out 3 on this side, and we're going to be multiplying by x minus 2 on this side. So then, we can just multiply this out, and then solve for x, which should be pretty easy. We just move x to this side and move constants to that side, and we're going to get x equals negative 19. And I just want to find the value of x. That's just negative 19. Next, we have in rectangle TUVW shown here, WX is 4 units, XY is 2 units, and YV is 1 unit, and UV is 6 units. What is the absolute difference between the areas of triangles TXZ, so that right here, and UYZ, so that thing right there? Do you see an easy way to do this, Bill?
Okay, so we're looking for areas of triangle XYZ and UYZ. Well, um, so the absolute difference. Okay, so if you look at it, the triangles TXU and the triangles TYU are the same area, right? And if you take T triangle TZU from TXU, you're left with TXZ. And if you do the same for TYU, you're left with, UYZ. And so it's the same area minus the same area, so those two actually have the same area,
Yeah, okay. That
TYU.
was actually a very good yeah, that was a very good observation. So okay, let me I don't know, like write it out a little bit more. So what Bill is saying here is that we have the triangles TXU shown here and another triangle TYU right here. Now these triangles have the same area. Why? Because they share the exact same base and they also have the same height, right? Which is just the width of the rectangle. So these have the same area. Okay, if these have the same area and we subtract this same area from both of them, TUZ, the remaining parts are going to have the same area. And that's just the triangles that we have, right? That we're looking for the absolute difference between the areas, right? And if they're the same area, then the absolute value between the areas is just 0. So that's your answer. Um, yeah, it's totally fine if you join late or anything. Yeah, I mean, like we're just doing problems. It's not like we're teaching a lesson. So it's basically like totally fine if you if you like join in and out. And we'll also be posting the recording of our meeting, so you can always look at the stuff that we've done before. But yeah. Okay, let's move on to number 7. A bag contains 4 blue, 5 green, and 3 red marbles. How many green marbles must be added to the bag? So that's 75% of the marbles are green. Okay, so basically, the percentage of marbles that are green is going to be the number of marbles that are green, so number of green over the total number of marbles that we have, number of total. Right. So okay. So let's say X is the number of green marbles that we add to our bag. Now we can find expressions for our number of green and number of total things. So our number of green is just going to be 5 plus X, right? Because we start at 5 green and we're adding X green marbles. And our number of total marbles is going to be our number of starting total marbles, which is 12 plus X, right? Because that's the number of marbles that we're adding. Okay, so this is going to be the percentage. Well, this times 100 is going to be the percentage of our marbles that are green, right? But so this is going to equal 0.75, right? Because we want 75% of our marbles green, right? And then now we can just solve for X, and whatever X is, that's going to be our answer. So we can multiply both sides by 12 plus X. And now we can just multiply the 0.75 out. So 0.75 is just 3/4, right? So 3/4 times 12, you can get a 4 from 12, that's 3. So 3 times 3 is 9. And then we're going to have 3/4 X there. Oh, whoops. Okay. And then we can move all of our X to this side, all of our constants to this side. So we just have one x here, right? So one minus 3/4 is just 1/4. And we have 9, we have 5, so 9 minus 5 is just 4, so x is 16, so that's your answer. Okay, number 8. MD rides a three-wheel motorcycle called a trike. MD has a spare tire for his trike and wants to occasionally swap out his tires so that all four will have been used for the same distance as he drives to 25,000 miles. How many miles will each tire drive? Okay, so he's going to drive for 25,000 miles, and he has four tires, and all four tires are going to drive the same mile amount, and three tires are going to be driving at the same time. Okay, so you can think about the total amount of miles for the tires, not the motorcycle, is going to be three times 25,000 miles. Why? Because the motorcycle always has three tires on it, right? So yeah, it's just going to be three times 25,000, which is 75,000, right? So this is the total number of miles that the tires together drive, right? But we want to separate that equally between four tires, right? So that means for each tire, the total number of miles driven is just going to be this divided by four, right? So we just divide this out. That's going to be 135. So what, like 8, and it's going to have 3, and 30 has 28, which is 7, and then 20, which is 5. Okay, so then we have 18,750, and that's your answer. Anything you want to say there, Bill?
Right. So for that problem, you also could have just if you thought about it, each tire will be used 3/4 of how much it like would have used if there was only three tires. So, you could have just multiplied the original distance by 3/4 and gotten the same answer, basically.
Yep.
But I mean, that's in the end, that's pretty much what we did. We multiplied by
I
3 and
mean,
divided
yeah,
by 4.
that's the exact same thing that we did. Okay, let's move on. Number 9, Lucy and her father share the same birthday. When Lucy turned 15, her father turned three times her age. On their birthday this year, Lucy's father turned exactly twice as old as she turned. How old did Lucy turn this year? Okay, so it's saying that once, when Lucy turned 15, her father turned three times her age. Well, her age is 15, so that means her father turned 45 when Lucy turned 15. Now, with ages, the separation between two ages is always going to stay the same, right? Or like if you share the same birthday, um, right? Because like every year you go up by one, but the difference is still going to be the same. So the difference between the ages is 30, right? So that means the difference between their ages always has to be 30. And let's say x, so we have some condition there, right? So let's say x is Lucy's age when that condition is satisfied. That means her father's age has to be x plus 30. Now, what is our condition? Our condition is that Lucy's father is twice as old as she, which means that 2x has to equal x plus 30, and we just solve for x equals 30. So Lucy had to have turned 30 that year, which is our answer. And you don't have to put it into a formula. Also, I mean, you can just think of it with the difference directly, right? Like if if Lucy's age is something and her father's age is 30 plus that something, and but her father's age is twice as large as her age, well, her age has to be the same as the difference, right? Because the difference is going to add the same as her age, which is going to be two times her age. So then her age just has to be 30. Anything you want to say, Bill?
Right. So what Austin said is very true. A lot of stuff when there's a lot of stuff that can be solved that it should be solved with just by setting up system equations and things like that. But a lot of the times you just think about the numbers, like in this case, just thinking about the difference. You won't actually have to go through the process of setting up an equation and doing all that. You can just kind of think
I
about it
mean, yeah, but I mean, like you can do it both ways. Setting up the equation isn't hard at all either. But yeah,
like, but like
I
it
mean,
might take a bit more time. So just
okay. I mean, it's whatever. On the actual test, you probably shouldn't think of too much like what method should I use, right? Because
right. So just
that's actually going to
basically
take.
do the first thing
Just
that comes to
do,
mind.
yeah, just do whatever. Just do the first thing that you
As
think
long
of.
as it works out logically, just basically you should do the first thing that comes to mind and not waste time thinking about it.
Yep. Okay, number 10, the sum of three distinct two-digit primes is 53. Two of the primes have a units digit of 3, and okay, the sum of three distinct two-digit primes is 53. Two of the primes have units digit of 3, and the other prime has a units digit of 7. What is the greatest of these three primes? Okay, so when it asks what is the greatest of the three primes, I mean that's basically saying that we only have like one solution of three primes, right? Or all of our solutions are going to have the same greatest of three primes, right? So basically, we just had to find one solution and then find the greatest prime of that solution, and that's going to be our answer. So we have two primes that have a units digit of 3, and then one prime that has the units digit of 7. All right. I feel like testing primes would be totally okay here because it doesn't seem bad at all. I mean, or we can say or we can find out what the sum of the tensor digit has to be, right? So if we add just the units digit together, we're gonna have 6 plus 7, which is 13, right? And if we subtract that from 53, that means we're gonna get 40. So that means all of their tens digits has to add up to 40, and all we have to do is we have to find tens digits for these units digits that will make them two-digit primes, but that the tens digits also sum to 4, right? So I mean, we can just try 13 and 23 and 27, but that's not 27, 17, because that would add up to 4 because it's 1, 2, and 1, and we can see that those actually make primes. So then that's just one of our solutions, or it could be the solution, but we just need to find the greatest of these primes, which is 23, which is just our answer. Um, I mean, I don't know, the putting tens digits should be pretty easy because you know that it can't be like, I mean, it has to be 1 or 2, right? Because the other ones also have to be 1 or 2, and they have to sum to 4, right? So you can only test 1 or 2, and they're distinct, right? So you can't have 1 and 1 on the 13 on the 3. So you have to have 1 and 2. So the other one has to be 1. So yeah, anything you want to say, Dogo?
Right. Nah, that's fairly simple. That's fairly simple problem.
Yeah.
There's
Let's move
no.
on to 11. Okay, Ross and Max have a combined weight of 184 pounds. Ross and Seth have a combined weight of 197 pounds, and Max and Seth have a combined weight of 189 pounds. Sorry. How many pounds does Ross weigh? All right, so we just have like three equations here with three variables. So it's a system of three equations, and we just need to solve for that. So let's say Ross's weight is X, and Max's weight is Y, and Seth's weight is Z. So then we should set up our equations. So Ross and Max, their combined weight is 184. Ross and Seth is 187, and Max and Seth is 189. Okay, and we just need to solve for this. You can solve this in a bunch of ways. Let's just do let's take this equation and subtract it by that equation. So if we do that, we're gonna have z minus y, and it's going to equal 187 minus 84, so that's just 13. And then we also have y plus z is 189. So what can we do here? Well, we can add both equations. So then we have 2z equals 13 plus 189, which is just 202, right? So then z is just going to equal 202 divided by 2, which is 101. And then now you can use like these to solve for x and y, right? So x is going to be 187 minus 101, which is just 96, and y is just going to be 189 minus 101, which is 88. So again, you can solve this in a bunch of ways. Like, okay, yeah, like, uh, hold on. So yeah, you can do this in a bunch of ways. Yeah, okay. Anything you want to say there, Bo?
Right. So yeah, things like this have you can do a lot of different ways. Just
Yeah,
whichever way you're most comfortable with, whichever way you think of first. It
yeah,
should be the one to should be the one you do. Thinking of faster ways to do it, a lot of the times will waste enough time that it's not worth it. So just do whatever you can think of first.
yep. All right. Let's move on to number 12. What is the least possible denominator of a positive rational number whose repeating decimal representation is 0.ab, where where a and b are distinct digits and a b is repeating. Okay, so basically we have like a decimal representation of 0.ab, and so on, right? We want to find, and this corresponds to some fraction. We don't know what this fraction is, but we want to find or like there are multiple solutions for that fraction because we don't know anything about a and b. We want to find the least possible denominator of that of this fraction. So okay, so I mean maybe we can start off by thinking uh wait okay, A and B are distinct digits. Never mind. So I was gonna say maybe we could start off by thinking that 1/3 would work here, but A and B had to be distinct. So okay so we can think of the fraction thingy that I've always used before, which is if you have if you have like a oh man, I don't want to I don't know. So like if you have a repeating thing, a repeating decimal thing,
Oh, with a repeating thing.
what?
Okay, never mind. Yeah, never mind.
Yeah. So yeah, so like so my thing with the repeating decimal stuff is it's I don't know, but so like you look at the thing, right, and you you look at the thing, and the number of oh my god, the number of digits that are under the repeating thing, you want to have a 9 for each of those in your denominator. So we have two repeating things. That's going to be 99 in our denominator, and our numerator is going to be our repeating thing minus our non-repeating thing. But we have no non-repeating thing here, so that means it's just going to be AB. So like if we had 0.2 AB repeating, but just the AB was repeating, well, I think you would say we have nines for the A and B, but we have a zero. We have a zero for each non-repeating thing that we have. So we have one non-repeating thing, and then we have our numerator is going to be our repeating thing minus our non-repeating thing. So two, yeah. And but like if we had a 23 here, then we would subtract 23, and we also have another zero. But you can also solve this by like the more what I don't know the like an more proofy way by multiplying this by like if we say that this equals x, we can say that 100x is going to be ab dot ab repeating, right? But the dot ab repeating is just x, right? So we can just say 100x is ab plus x. So then 99x is ab, which is saying what x is ab over 99, which is the same thing that we got before. Okay, now we want to find um we want to find the least possible denominator that this can be, right? And it's not just 99, right? Because AB can be something where it simplifies the 99, and we want to find what can the 99 simplify to. So okay, but so A and B have to be distinct digits, right? So 99, it has it has factors of 9 and 11, right? But we can't have any factor of 11 as A and B, right? Because any factor of 11 has the same units digit and tens digit, right? So basically you can't ever cancel out this 11. So if we can't ever cancel out this 11, we want to try our best to cancel out this 9, and that would give us our like least possible denominator of 11, right? And that's possible, right? If we had A and B as 0, 9. So, and this would be our best case scenario, or this would give us our least possible denominator, right? Because again, we can't cancel out this 11. So 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 yeah, this would be our best fraction. So then we just have 1/11. So our least possible denominator is 11. Anything you want to say there, Bill?
Right. So yeah, Austin really hates explaining the repeating fraction thing. But yeah, just something to that's just something you should really remember is converting from a repeating decimal to a fraction is just putting it over 99, over however many times that is repeating.
Yeah, yeah. That's a repeating decimals and fractions come up pretty often. So yeah, if you don't know those, then know those. All right. Number 13, a taxi charges 3.25 for the first ride and 45 cents for each additional 1/4 mile thereafter. At most, how many miles can a passenger travel using 1360 express your answers? Mixed number. So, I mean, okay, if you're traveling with this taxi, you're first going to pay 3.25, right? I'm not going to care about the dollar signs. I'm just going to have everything as dollars. So if you ride with this taxi, you're going to have to pay an initial amount of 3.25, and every 1/4 mile that you drive, you're going to add 0.45 for each additional 1/4 mile. So if we say X, uh, yeah, sure. Let's say X is our each additional 1/4 mile that we drive, right? So then our the total money that we pay on this taxi is going to equal this amount. But we want to find the number of miles that a passenger can travel with a set amount of money, right? So we can set these equations equal to each other and solve for x, and x would be the greatest amount of miles uh, that we can drive with a taxi. So then you just uh, you just solve for x, right? So you minus 3.25 on both sides. So then you have 10.35 here, and then you just divide by 0.14. So if we're dividing this by 0.14, we can multiply by 100 on both sides, or both top and bottom, right? So then we can have this, and then what? Okay, we can try maybe try dividing this by 7. See if that will work. Then we would have 1 and 33, which is 4, and then we have 5, but that doesn't work. Okay, so then we just say x equals uh then we just sure let's just say x equals this for now. Um, but x is each 1/4 mile that we drive, right? But we want to find the number of miles that we can drive, right? So if we have this amount of 1/4 miles, um, the number of miles that we can drive is going to be this divided by 4, right? Uh, have I done something wrong?
We're uh, how did you get 0.14?
How did I get
How did
0.14?
you get
What
0.14,
the?
Austin? I would like to know also.
Oh, I have no idea actually. How did I get
How did
0.14?
you get 0.14?
Okay, it's obviously not
It
0.14, okay?
obviously isn't.
It's 0.45. Um yeah, I have no idea. But we're paying 0.45 for every additional 1/4 mile, right? So it has to be 0.45 here. So 0.45 here. So dividing by 0.45, so that means we're dividing this by 45. Okay, and then we can get a 5 out of top and bottom, right? So then we have 7/9. Okay, and then the top is divisible by 9, right? Because it's digits sum to a multiple of 9. So we're gonna try dividing it. So that would be 23. So we drive 23 1/4 miles, but we want to find the number of miles that we've driven. Well, that's just going to be this amount divided by 4, right? Um, uh, so it's going to be this amount divided by 4, right? Because if we drive like 4 1/4 miles, then we're driving 1 mile, which is just 4 divided by 4, right? Okay, so this is our answer, but not our final answer because it wants your answer as a mixed number, right? Um, so that's just what 5 3/4. No, 6 3/4. No, 5 3/4. Did we do something wrong? Oh boy.
Yeah, because you had to because you like that's taking the first 3.25
Oh,
the
okay. Yeah, yeah. Okay, I see it now. Yeah, sorry. I missed the taxi charges 325 for the first mile, when I was thinking that it just starts charging 325 for like 0 miles, and then it charges stuff. So like basically we're going to have an extra mile here, right? So doing this, we have 5 3/4 miles, but we actually get our we get a first mile from our 325. So this is going to be the number of miles that we drew. So it's just going to be 6 3/4. All right. Anything you want to say there, bro?
Right. So, first of all, don't be dumb like Austin. And yeah. Uh,
Yeah, that was really weird.
right. So basically, realize that it's every 1/4 mile because I feel like that's a mistake that might be made if you're thinking so fast. Is yeah, you just have it as in miles and not mixed miles. But otherwise, that's not that much of a problem. So yeah.
Yeah. Okay. So let's move on to the next problem. Um, Callie is mixing soil for a container garden. If she mixes 2 meters cubed if she mixes 2 meters cubes of soil containing 35% sand with 6 meters cube of soil containing 15% sand, what percent of the new mixture is sand? All right, so we're adding so we're combining 2 meters cubed of soil, and it has 25, no, not 25, 35% sand. We're combining it with 6 meters cube of soil, and it has 15% sand. So we're going to end up with 8 meters cube of soil. And we want to find the percent of the new mixture that is sand. Okay. So what we can do here is we can find the amount of sand that will be in this mixture. And then we divide that amount of sand by the total volume of the mixture, which is just 8 meters cubed. And we can find the amount of sand that is going to be in this mixture by finding the amounts of sand that are in each of these things. And we can do that by just like multiplying 0.35 by 2 and 0.15 by 6, right? So if we do that, then we're going to have 0.7 meters cubed of sand in here, and we're going to have what 6 so zero point 0.9 meters cubed of sand in here. So all of this amount of sand has to be in this, right? So that means the amount of sand that we have here is going to be 1.6 meters cubed. And then to find the percentage of sand, that's just going to be this divided by 80 meters cubed, which is just 0.2. And then convert that into percent, that's just 20%, which is our answer. Anything you want to say, Dippo?
Right. So yeah, that's not really anything that difficult. You're just finding the, it's just multiplying and then adding. So yeah. Hi is asking, wait, how did you do it that way? So we just found how much sand there is, and then we put it over the total amount of the total amount of mixture there is, and that basically that's how we find it.
Yeah. Um, yeah, there are probably multiple ways to do this. Abhinav, why are there only 6 people? Well, there are only 6 people.
There's only six
Yeah.
people. Yeah.
Um, you were saying in the other meet, I think you were saying if you like you couldn't hear us, can you hear us now? Okay. Yeah. We just have 6 people. Uh, okay, so let's move on to the next problem. Alex can run a complete lap around the school track in 1 minute and 28 seconds, and Becky can run a complete lap in 1 minute and 16 seconds. If they begin running at the same time and location, how many laps will Alex have run when Becky passes him for the first time? Okay, so Alex runs a complete lap in 1 minute and 28 seconds. Let's just do everything in seconds, which will probably make things a lot easier. So 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 this would be Alex completes a lap in 88 seconds, and Becky completes a lap in 76 seconds. So we're looking at when Alex and Becky passes for the first time. So um, so okay, when they pass for the first time, so Becky is faster than Alex, right? Because she runs a lap in a smaller amount of time. So when they pass for the first time, that's going to be when Becky has run exactly one more lap than Alex has. Because then like they would overlap, right? And then they would pass him. So maybe like we can just set up an equation, right? So like if we say X is the amount of time that it's passed, the number of laps Alex will have run is X over 88, and Becky is X over 76, right? And when they pass, Becky is going to have run one more lap than Alex has, which means X over 76 is going to equal X over 88 plus 1. Okay, and now I can just solve for X. So I don't know. Maybe we should just multiply by 76 and 88. So then we have 88x equals 76x plus 76 times 88. And we can just leave it like this for now, and then like expand it later. So move x to the side. So then we have 12x equals 76 times 88. And that means x is going to equal 76 times 88 or 12. And so we can get like we can cancel out a 4 from 88, so that would be 22. So then we have 3 here, and then Oh, okay, so I think this might be our correct time. So right now we're saying the amount of time that has passed when they meet is going to be 76 times 22 over 3. But we actually want to find how many laps will Alex have run. So to find that, we would just do this amount of time over 88, right? So then if we divide this by 88, then we can cancel out 22 from 88. We would have 4, and we can cancel out a 4 from 76, and then we would have 19. Okay, so the amount of laps that Alex will have run is 19 over 3, but we only want to find the complete laps Alex has run, right? So if he's run 19 over 3, that means the number of complete laps he's run is just 6, right? Because that's the largest integer that is below 19 over 3. Yeah. Anything you gonna say there, Bill?
Okay, so this is doing it algebraically. The way I would go, I don't know if most people do this, but something I would be thinking about is so for Becky to run one more lap than Alex, Beck, which is, Becky pass him, is Becky has to run one more lap. And so if we look at this, Becky, for each lap, Becky takes, what, 12 seconds less than Alex to run each lap. And so we want Becky to gain a lead of 76 seconds, which is how much she runs, how much time she takes to run a lap. We want her to gain a 76-second lead. And so we see that like it will take her what? It will take her more than 6 laps to do it, but like between 6 and 7 laps to do it. So she will pass Alex between between six and between her 6th and 7th lap. And so Alex will be on his 6th lap, I think. Right?
Yeah,
Yeah.
yeah,
Wait,
yeah.
no, she
6
will
is
pass
correct.
him on.
But
She will pass him
oh,
on her what? Between After she finished her 7th lap, she will pass Alex. And so if she's on her 7 point something lap and she passes Alex at that point, then Alex will be on his 6th lap. Alex will have completed 6 laps.
yeah, yeah. That's a good way to think about it. Yeah. All right, let's move on to number 16. The Beavers, Ducks, Platypuses, and Narwhals are the only 4 basketball teams remaining in a single elimination tournament. Each round consists of a team playing in pairs, with the winner of each game continuing to the next round. If the teams are randomly paired and each has the equal probability of winning any game, what is the probability that the Ducks and the Beavers will play each other in one of the 2 rounds? Express your answer as a common fraction. All right. Yeah. Okay. So they're first sorted randomly into the bracket, and then each of them, or when they play, they also have a random chance of winning, or both both teams have the same amount of chances of winning. We want to find the probability that the Ducks and Beavers will play. So the simplest way I can think of doing this is casework, right? Um, what do you think, Bill?
Sorry, how are you trying to do it?
Casework.
Casework. So, right. So casework, casework would right, case work would probably work, honestly. So,
Well, yeah, it would work, but
yeah.
like,
And
is that the
in this
best way?
case,
Yeah.
much. There's not really like that much cases. you could probably do casework because there's just
Yeah, there's
not
only
that
two
many
cases.
to
Yeah,
worry about. Think about.
yeah. All right. So, I mean, but okay, so there are only two cases we have to consider, right? The two cases that we have to consider is if they meet in the first round and if they don't meet in the first round. So, okay, what's the probability that they meet in the first round? Well, we have four teams: the beavers, ducks, platypuses, and narwhals. Um, Now, if they are so they're going to be in some random order, right? And let's just say that the first two that we have in our list is going to be like is going to be paired together in the first round. So the total number of permutations that we can have this list to be is 24, right? Which is just 4 factorial. 4 coming from the number of elements we have in our list, and it's just 4 factorial because we're sorting all of them and we're looking at permutations, right? Okay, so and then we can try to see how many of those permutations does the beavers and the ducks ha- we can look at how many of those permutations that have beavers and ducks paired together in the first round. Um, and that's going to be so one we can have right here, right? Um, but another we can have these two switch, right? But but another we can have these two switch, right? And that would correspond to 2 more of these, right? So far that's already 4. And then we can have this also in the bottom, right? And that wouldn't like mirror everything, so that would be twice as much as this. So then we have like 8 of those working here, right? So that means the probability that they appear together in the first round is 1/3. So, and if they are paired together in the first round, that's all we have to consider, right? So that gives us already an initial 1/3 chance of them pairing together in the first round. So now, what if they aren't paired? Well, the probability that they aren't paired is 2/3, right? It's just 1 minus 1/3, and we want to find the probability that they will play together in this condition. Well, for them to play together, so they're going to be in separate brackets, right? So like maybe the ducks are here and the beavers are here. So for them to play together, they both have to advance on to the second round, and then they'll play together, right? And the probability that that will happen is just 1/4, right? Because all the teams have equal chances of winning. The chance that the ducks will win here is 1/2. The chance that the beavers will win is 1/2 here. So then the probability of them both winning is 1/2 times 1/2 or 1/4. So then this is just 1/6. So then we add our probability of 1/3 plus 1/6, which is just what 3 uh 3/6, which is 1/2. Yeah, that's your answer, 1/2. Um, anything you want to say there, Paul?
Right. So in this problem, there isn't that much. There isn't that many cases, so it's fairly easy to just test all of them. So, if you were reluctant to do casework, just remember that this for problems like these, it's probably faster to just bash it out casework using casework because there's just not that many cases.
Yeah, but there's also like not much else to go off of. So
Right.
I,
Like in
I
this
I'm
case, if you're
thinking,
trying to do it more like rigorously, you might be there while trying to think of a way to do it. So it's more worthwhile to just do casework.
yeah, the casework was fun, and it's probably the best way. So yeah. Okay, let's move on. Number 17. A function x, f of x, is defined for all positive integers. If f of a plus f of b equals f of ab for any two positive integers a and b, and f of 3 is 5, what is f of 27? Okay, we can try to set up multiple equations here, right? So let's try f of 3 being on this side. So we get f of 3 plus f of b it's going to equal f of 27, and then we can try to do some stuff here, right? So so first looking at our thing here, this would be saying that p has to equal 27 divided by 3, right? So then we're saying f of 3 plus f of 9 is f of 27. So, but we have the values of f of 3 and f of 27, right? Which means we can solve for f of 9. Oh wait, what? No, never mind. I'm bad. We don't have the value of f of 27. But we can say that 5 plus f of 9 is f of 27. So if we find the value of f of 9, then we can find the value of f of 27. So, but we can find the value of f of 9 by using this thing again, right? We can say f of 3 plus f of 3 is f of 9, which means that 5 plus 5 is f of 9, which means that f of 9 is 10, which means that 15 is 27. So that's just our answer. Anything you want to say, Dopo?
Right. I mean, this isn't that bad of a problem, so I think it's fine.
Yeah. All right. Number 18, rectangle ABCD is shown with AB equals 6 units and AD equals 5 units. If AC is extended to point E such that AC is congruent to CE, what is the length of DE? All right. Okay, so what we can do here? Well, okay, first I'm going to draw it here. So we're going to have AD is 5, AB is 6, and AC is here. So we're extending AC to E such that AC is congruent to CE, which means that they have the same length, right? And well, what's the length of AC? We can find that from the rectangle, right? Well, with like the Pythagorean theorem. So then the length of AC is just going to be 25 plus 36 rooted. So that's just 61 rooted. So the length of C also has to be root 61, and we want to find the length of DE here. Um, we can find it with actually okay, yeah. Yeah, so like Hi saying, we can extend AD all the way here, so that it connects with E to form a right angle. So then this side length would have to be this side length would have to be 5, right? Because if we look at ADC, okay, let's call this point I don't know. Let's call this point F. So if we look at this, ADC is similar to AFE, right? And AC is half long as C, right? So AD has to be half as long as AF, right? Which means that this length is just going to be 5. And what we can do is we can find FE from this big triangle AFE with the Pythagorean theorem, and then we can use the Pythagorean theorem again to find the length of DE. So okay, so we're going to have 2 times 61 squared is going to equal we can just go ahead and say that it minus 25 rooted is going to equal f of e, or FE. And this is just going to be 4 times 61, not 25, sorry. It's going to be 100, right? Because this side length is 10, so 10 squared is 100. And then this is just going to be 4 times 61, which is 242. No, 244. Yep. and it's going to be minus 100 and the rooted. So that's just 144 rooted, which is just
Hey,
12.
Austin,
Yeah.
if you haven't noticed, ABC and AFE are similar triangles, so you can just use that to find FE equals 12, because DC equals 6. And so
Wait,
you,
what?
because DC equals 6, right?
Yeah.
And
Oh, yeah, you can
ABC
just
equals
do it like
6.
that.
Yeah, you can just do it like that.
Okay. Okay, well, yeah. Okay, sure. Um, yeah. Okay. Okay. Well, if we continue like this, we find that FE is 12, and then TFE is just a 5, 12, 13 triangle, right? So then our answer is 13. But like Bill was saying, there's a bit of an easier way if we just look at ADC is similar to AFE again, but we already have the value of DC, so then you can just multiply by 2 to get 12, and then you have 13. Okay, anything else you want to say, Bill?
Oh, yeah, no, now.
All right. The digits of a three-digit integer are reversed to form a new integer of greater value. The product of this new integer and the original integer is 91,567. What is the new integer? Okay, so yeah, similar triangles are powerful. Okay, so let's say we have a three-digit integer ABC, and ABC are digits. Why did I write equals? So we're reversing it to CBA, right? And this is our new integer. So first of all, we're saying that ABC times CBA is equaling 91,567. And okay, and we're just saying that. And we want to find what the new integer is. So the first thing I can think of, maybe, is to work with the units digit. Um, maybe yeah, okay. Or so um or C times A doesn't have to be necessarily 7, right? Like C times A can also be like 27, right? And the units digit would still be 7.
Right, yes.
Yeah. So okay, so yeah. So if we look at units digits, we see that C times A has to be some number with a units digit of 7, right? So C times A can be 7, but it can also be 17. But 17 is prime, so we can't have that. Or like 17 is prime, but it's also bigger than 10, so we can't have 17 and 1. So we don't have 17. We can't have C times A is 27, and anything else is too big, right? So if we look at C times A is 7, then C and A is either 7 or 1, right? And if we look here, then C or A is going to be 9 or 3, right? Um, okay. So these are like okay. So then we can just test these, right? It's only like wait okay, a new integer greater value. Okay, so we can just test these, right? It's only like two cases, right? Sure, let's just test them. Yeah. So let's say so let's first test C and A being in the set of 7 and 1. Well, C has to be 7 and A has to be 1, right? Because our new integer has to be a greater value, right? So then C would be like 700, uh, and A would be corresponding to 100, right? So like if we had 7 and 1, then C has to be the bigger one. So then we have 1B 7 and 7B 1, and then they multiply to 91,567. So what should we do here? One way that I'm thinking of is we can say that when B7 is just 107 plus 10p, and we can multiply this by that, which is, yeah. Um, sure, okay, let's just go ahead and do it like this. Or what do you think, Bill? Do you think there's a better way to do this?
Mm, okay. I mean, yeah, there's not really that good of a way to do it, I guess. If you're just trying out the cases, like you're gonna have to like just multiply them. I mean, you could try to represent them and then just have B, but
Also,
I think that will be
also,
complicated.
also we can rule out this case, right? Because if we had
Right, because yeah,
okay, so it would have to be 3b9 and 9b1, right?
right.
And if we look at the like
Yeah,
the value of
the
this,
1500 figure, that's not.
yeah, that's way too small, right? Because
It's
if we
way too
just
big.
multiply the 900,
It's way too
oh,
big.
what? No, I'm saying this is way too small. And this is way too big.
Yeah.
Okay, so if we just multiply the 900 by this, that would be um we had two zeros on the end, and then like 27 times 9b, okay, and then another 20, or yeah, and then 81 stuff, right? But okay, that's like way too big, right? We have this is we know that we have to have at least 27 27 followed by four zeros, which is already way too big, right? um okay, yeah, so do you just want to like do it like this?
Um, I guess that could work, I guess. Right,
Yeah,
so
maybe testing digits would also
yeah, just
work.
testing
uh,
some of the numbers to get a rough idea. I think you can do that.
Yeah, I don't know. But okay, maybe we should just try both ways. So let's
Yeah,
just go ahead and do
I
that.
think in this case you'll be safe with just trying numbers and trying to find and just finding like a general area, just like getting an idea of where the number might be, and that way you can test it.
Sure. Okay, so like we can start by
Right,
thinking
like
that it's
that. Yeah.
5, right? And then we just multiply it, and so we're gonna get what some stuff. Okay, I'm just gonna multiply on my calculator because I bet you guys can multiply. So then you get 117907,
You guys better
and
be
this is
able
too
to
big.
multiply.
Okay, so this is too big, right? So as to go lower, maybe we should test 3 now. Yeah. So if we multiply that out, then we get 100147 for sure. So then let's try 7. Let's try 1. Um, so then um, then we have too small of a number, 83187. So then we know it has to be 2. So then, yeah, so when we use 2, then we have 91567. So it has to be 721 and 127. So that way is not too bad, I guess. I mean, you only test like like 3 or 4 maximum cases. Um, should we also try the expansion way?
I mean, you could, but in my opinion, I think the expansion way would take a while. In this case, there's, I mean, there is like the calculations are fairly complicated. Yeah, like Haha said, it's a waste of time. Doing the expansion way, it will take a while. It's rigorous, but just testing cases in this case, and you can get a general idea from the cases of like where the result would be. So I think testing in this case would be the better solution.
Yeah, sure. Yeah, yeah, it's not too bad. So then our new integer, which has to be our greatest integer, is going to be 721. So that's your answer. Okay. Oh, you're 101. Okay. Okay, so number 20, we have diagonal xz of rectangle wxyz is divided into three segments, each of length 2 units, by m and n as shown. Segments mw and ny are parallel and are both perpendicular to xz. What is the area of wxyz? Express your answer in simplest radical form. Okay, so we want to find the area of the rectangle. Yep. So let me draw it first. So we have wxyz, and then we have xe here. The total length of this is 6, and we have two parallel segments here. It's going to divide it into 2, 2, and 2. These points are m and n. And we have to find the area of the rectangle. All right. Um, so what can we do here? We also know that segments MW and NY are perpendicular to XC, right? So then we have like that. Um,
Okay, so first of all, we're looking at areas here. So since we're looking at area, like something you can know is that the two triangles will add up to the area of. Wait, no, never mind. Ignore that. Ignore that. I did something wrong there. So.
mm, um,
Right, so like 1001 said, corner bash is a viable option, I would think. I would think. But it would be a lengthy, it would take a bit of time. It's corner bash will be, bashy.
Um, what if we tried making this triangle, but 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 this line is parallel to this line. Uh,
Uh,
we can also divide this into
right.
two
So
triangles.
if you do that, then there are a lot of congruent and right. There's a bunch of congruent triangles if you do that.
Okay,
And
so
from what it seems like, if you do that, actually, never mind. Yeah, never mind.
um, okay, so what if we tried saying that this angle is A and this angle is B? Um, so then this angle would be 180 minus A minus B. Um, this angle. And so this triangle is congruent to this triangle, right?
Right. Yes.
Which means that I mean this angle. Well, yeah, this angle has to be that as well. Um, okay, well, this angle would have to be I'm not sure if this is getting us anywhere.
So I think what we should be looking at is this thing has some like special features, I guess. Like the thing that's defining this rectangle is the fact that when you draw perpendiculars on the trisectors, it intersects the
Yeah,
segments,
yeah.
and so that's like the important part of this graph. Otherwise, you can just like find some random rectangle that fits this. So this is, I think that's a part where we should be looking at. And also, if you notice, there are a lot of similar triangles in this case. XMW is similar to like every triangle in here is similar to each other basically. So that's also something worth noting. Practically every triangle in here is similar with each other. So yeah. And
Um,
also you can rearrange this, you can rearrange this graph into a rectangle, I guess. You can rearrange it into a rectangle, but I'm not sure how much that would help.
so would these two triangles be congruent?
Yes, they would, because they share a side
Um,
length and they share angle measures.
oh, which angle measures?
Um, so in this case, well, you're drawing that line parallel, right?
I'm drawing this line parallel.
Right, if you're drawing that line parallel and you're drawing that line as a bisector, so um, well, they share a side and also like the uh, the two diagonal lines are parallel, so you can use that.
Wait, what?
The two diagonal lines that are perpendicular to the main diagonal line they're parallel, and so they share a side, and they you can use the parallel side.
Wait, what are you saying?
Like the lines, like the two diagonal lines, they're parallel,
Yeah,
right? Okay. And so those two are same, I guess.
those what those two? What I don't understand.
Okay, so okay, like the angles, the angles, right?
Of what?
Um, the triangles.
Do you want to write it on your whiteboard?
Okay, sure. Let's do that. All caps. Undefined interval. Okay. So, alright, let's draw this bad boy. Boom, 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 boom. That's
Yeah, okay.
simple, right?
If you see the side lengths are x and y, well, you can find one equation by saying x squared plus y squared is 64 from Pythagorean theorem.
Oh, that is terrible. Oh, that is terrible. Okay. But this is just a demonstration. We don't need a perfect graph for this. Alright, alright. So, first of all, they share this side, right?
Yeah.
And this side, this is constructed parallel to this. So,
So,
okay, okay, time for some advanced mathematics. This is perpendicular? Okay. So, because these are perpendicular, okay, okay, so, first of all, we know this angle equals this angle, right?
well, okay, that would be saying that'd be saying the like the side length are parallel, right? How do you know that?
Sorry, what? That would be saying which side and which side
Um,
are parallel? Or what?
these two.
Well, no, because, because, look,
Wait, what?
because this line and this line are parallel, right? These
Yeah.
two lines are parallel. You see it?
Okay. Okay. Yeah.
And also,
Oh,
we need to
well,
prove one more angle, right? We need to prove one more angle. And so now, so we can use, um, so you constructed this and this to be parallel, right? And so this equals this, and also um, this, and also this would equal this, because you know it's a parallelogram. And so, I'll do that.
well, okay. So these two lines have to
Right.
be
So,
parallel, right?
wait. Sorry. What?
Okay. So like, so so you have the uh actually wait. Um,
Actually, okay. Yeah. Go.
okay, well, okay, so like you said, these angles will be congruent from these two parallel lines and and this line, right? And
Right.
these two angles will be congruent as well. Um,
Actually, so
so
at this point, would they be? Would it be?
wait, what?
Oh
Oh
yeah.
wait, no,
Okay. Wait,
Wait,
actually, we haven't proved
no,
that.
okay, no. Those what?
Have we done that?
What?
Um, because the angle that's bordering the main diagonal, the small angle that's bordering the main diagonal, we haven't proved that that's congruent to anything.
Um, what? Okay, well, we can't say that those two, this angle and this angle are congruent yet, right?
Right, we can't.
Okay. So okay, but from this parallelogram, um, it has to be a parallelogram, right?
Well,
Yeah, because like we're cutting off a section of these. Okay, so they're both parallel. Okay, so it has to be a parallelogram. So that means this has to be that angle, right?
right,
Um, okay. We also know that at least that these two angles are
right. Those two angles are
uh,
congruent.
those two angles are congruent. Uh,
Right, right. So we can't prove anything from this, can we?
yeah. Actually I don't think so. Like we're yeah.
All right, I don't think this is working out very well.
Wait, what?
I don't think this is.
Uh,
Yeah, what are we doing? We don't know what we're
no,
doing.
no. 101 is saying something.
Yeah. So he's saying, what are you guys doing?
No. Okay. So we're trying to see if these this triangle and this triangle are congruent. Not these two. Oh hey, we actually have a solutions manual. If you want to go ahead and look at that.
All right. Yeah, I think
Oh, not
he's
yet.
saying no, no, don't do it.
Sure,
Leave
we
it.
can try
Oh,
some more
okay.
stuff. Um, oops. Well,
Okay. So first of all, in this case, if you're faced with a problem like this, at this point, you should just skip it. Like a long time ago, you should have skipped it
yeah. A long time ago, we should have skipped it.
because it's you've spent way too much problem on it, way too much time on it, so you should have skipped it. And also, coordinate bashing in this case is a viable option, but coordinate bashing would have also taken a lot of time. So this is one of those problems that you should either just skip or like write down some random number and then come back to later because if you look at it and you have no idea how to do it, then that you shouldn't be trying. Like if you look at it and your mind is just completely blank, you shouldn't waste time just sitting there not doing anything. Okay.
Okay. Um. Okay. So these two angles are congruent, right? Okay. So so this angle has to be 90 minus it, right? Because that's 90, and this this angle would have to be that angle, right? because
Right.
so,
Yes.
so this angle is 90 minus it, but this angle is 90 minus that.
Right.
So
So yeah,
that's
those
these
are
two.
similar triangles. Yes.
Okay, so then we have this triangle is similar to this triangle, right?
Right.
Because we have two congruent angles, so the other angle has to be congruent as well. Okay, so what is this saying now? So then we have 2 over WM. 2 over WM is equal to WM over 4, right? Which is saying that A is WM squared, right? So WM is 2 over 2, right? Maybe.
um.
I'm pretty sure.
Wait. How did you get that?
Okay, so this, okay, XMW and WMZ are similar, right?
Oh right. No, I see. I see. I see. Okay,
And
I see.
so
Yeah,
2
I see
two over
now.
WM and WM over
Right. See
4
now.
are the
Okay.
same.
So once you
Okay.
get to that point, yeah, that's okay. Yeah.
Okay, so we can go ahead and find this side
Yes.
length, right?
Yes.
Which is Pythagorean theorem, which is 8 plus 16, which is 24, rooted, which is what? 2 root 6. And then we can just find this side, right? From Pythagorean theorem, which is just 36 minus 24, rooted, which is just 12 rooted, which is just 2 root 3. And then we just find the area by multiplying them, right? Which is 4 times 3 times root 2, which is 12 root 2. That's the answer.
Yep. That is
Wait,
the
but how did you
answer.
get those angles were right?
Wait, what?
How did you get like those angles were right
Well,
angles?
it stated in the problem that they were perpendicular.
Yeah, it's stated in the problem that,
Oh, I missed that.
yeah.
Yeah. Read the problem fully. You know.
Okay, well, there you go.
Yeah.
That's a way. That's a way to do it.
Yeah, that's a way to do it. Using similar triangle. All right. So I think we're a bit over time now. So
Oh
we're gonna
yeah,
stop that for today.
yeah. We were supposed to end at
Eight
what,
forty-five.
8:45.
Yes, sir. All right.
Oh yeah, okay. Let's also check out
Yeah. Let's also
their
check out
solution.
their solution.
Uh, are we on 18?
That was
On
20.
20. Uh, okay. Oh, okay. Oh,
Oh
they
shoot.
drew a parallel line there,
Right.
not there. Okay.
Right.
Okay. M X R is M P, no,
Right.
P R Y.
Right.
Okay.
Because they drew a parallel
Um, um, R P equals M N
line. Yes.
and M R equals N P. Triangles X M R and R P Y
Oh,
are
congruent.
congruent
Yes. By ASA and
by ESA.
yeah.
Um, so those angles plus 2 plus right angle, right?
Right.
Okay. And therefore XR is RY and MR is PY. Okay. We can also determine by a similarity that RPY is similar to triangle NYZ. RPY is similar to NY and Z. Okay, so they both have a right angle. Then we know that it's like what we did here, kind of. So like so we know that this angle and this angle are the same, right?
Right. Yes.
And we know that this angle and this angle are the same, right? And by using like the right angle stuff, so this is going to be 90 minus that angle, right? But with this right angle, that's going to be 90 minus that angle, which is just going to be that angle. So then this angle and this angle are the same. So this angle and this angle are the same. So that means this angle and this angle also have to be the same. So then those are similar. And then what? Oh, using this information. Okay, 2 over ny equals py over 2. Two over ny equals py over 2, yep. And then ny equals 2py, and then what is this? Oh, okay, if ny is 2py, then you can use the Pythagorean theorem there. I think that's what they're saying. Okay, well, okay, 4 is ny times py. Because, wait, okay, wait, wait, what? How did they get 4 equals ny times py?
Yeah. Just expand that.
How did they get 4 equals ny times py?
I think it's just from the equations, like
Right.
from the diagram. Yeah.
Oh, it's just from this.
Yeah, they're just solving the equation.
Okay, and then, okay, yeah. And then once you solve that, then you get 2 is py squared. So py is root 2. So ny is 2 root 2. And then you can use Pythagorean theorem to get zy and xy. Yep. And then, yeah, and then you can use that to solve for the area. All right. All right, yeah, that's another way to do it.
Yeah. I think in this case the better solution is just going with triangle form. I often did. But that's also valid.
Yeah, this way was, I think that's pretty good.
I mean, it took us a while. It took us a while to get there, but yes, that's a good way to do it.
It took us a pretty long while to get there, though. All right, well, yeah, we're pretty over time now.
All right.
But yeah, that's going to be all for today.
Okay,
I
thank you.
hope this was helpful, and yeah. So we'll be continuing this in our next meeting, which will probably be next Saturday.
Okay, bye.
Yeah, goodbye.